The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Good morning, good afternoon, and good evening, everyone. My name is Matthias Gröschel. I'm a resident physician in infectious disease at Charité, Berlin in Germany, and a research fellow in biomedical informatics at Harvard Medical School. I welcome you all today to today's AI for Good webinar by Cynthia Rudin from Duke University, entitled Simpler Machine Learning Models for a Complex World. I first want to say hello and thank my co-moderator, David Hillis, who's also a resident physician at Charité, who gladly accepted the task to co-moderate today. Dr. Rudin is a professor of computer science at Duke University. Prior to that, she received her PhD from Princeton University, and her lab develops interpretable machine learning models. Her research aim is to design models, predictive models, that are simple to use, simple to understand, and she's very interestingly not only focused on health, but also on criminal justice and energy reliability. Dear audience, you're all tuned in now to the neural network, and you have the option to ask questions in the chat. Please do so. We'll take questions to Cynthia after her talk. Keep them brief and concise, so it's easier to us to forward the questions. We will also log into the neural network after the talk, and then we can chat offline there. Okay, Cynthia, the floor is yours. Please take it from you.
Okay, thank you. Okay, cool. Okay, so my lab at Duke is called the Interpretable Machine Learning Lab, and one of my most important goals is to create machine learning models that are small enough to fit on an index card, yet are as accurate as the best black box models like deep neural networks. And you're probably thinking, is this for real? Can you actually do this? Because it would mean a lot for trustworthy and fair machine learning if you could do this. And the answer is yes, we can totally do this for a lot of important problems. And we now think we know under what circumstances you can do it, right? You can't do it for computer vision or speech, but you can do it for many, many other problems. So I'm gonna give an example. So a few years ago, there was a competition sponsored by FICO, which is the major credit scoring agency in the United States, as well as Google, MIT, Oxford, Berkeley, and others. It's called the Explainable Machine Learning Challenge. And they gave everyone a data set from FICO, and the goal was to predict whether someone would default on a loan based on their credit history. And they told everyone to create a black box predictive model and explain it because they didn't think it was possible to create an interpretable model with the accuracy of a black box for such a complicated data set. But several years after the competition ended, my team figured out that there are accurate interpretable models. You just have to look for them carefully. So just to tell you a little about the data set, it's got about 10,000 loan applicants from a particularly difficult subpopulation. And the goal is to use credit history to predict whether someone's going to default on a loan. And again, it uses data from the major credit scoring agency in the United States. And at the time, which was 5 years ago, no one produced a really tiny interpretable model that was as accurate as a black box. People produced tiny models, but they weren't accurate. And we produced something that was a combination of tiny models at that time, but the overall model wasn't tiny. But 4 years later, which was last year, we produced the first small models that performed as well as the black box models for this data set, because we had some new powerful machine learning algorithms that could do it. And because the models fit on an index card, they also fit on a PowerPoint slide. So I can show them to you. So the first model that I'm going to show was produced by the fast sparse algorithm from our lab, which creates sparse generalized additive models. And this is work with Jiachong Liu, Chudi Zheng, and Margot Seltzer. And this is the whole fast sparse model for the FICO dataset right here. And so the way it works is that you get a score for each of these features, and you just add up the total number of points you get from each of the features, and that total number translates into a risk for defaulting on a loan. So let's take a look at some of the factors here. So months since oldest trade open. So if your oldest trade is very recent, like within the last 100 months, then you get more risk points because you're riskier. And then if the number of satisfactory trades is very small, if it's not so good, then you get more risk points. Now, external risk estimate, this seems to be kind of a really good feature, and it's especially sensitive between values sort of 60 to 80. Okay, so what's really shocking about this model, besides its simplicity in describing this very difficult benchmark data set accurately, is that we created it in under 4 seconds. Right, and that's how fast this algorithm runs on average for this data set. It's usually about 4 seconds. Right, it used to be that finding interpretable models was so computationally expensive that we just couldn't do it at all. And now we can do it in just a few seconds. So let me show you a different type of predictive model for this data set. This one's going to be a sparse decision tree. It's created by the GHOST algorithm. GHOST stands for Generalized Optimal Sparse Decision Trees. And it was developed over the course of a decade. And I'm just put pictures of the army of people we have that have worked on GHOST. So GHOST is really fast, it's order of magnitude faster than previous approaches. And so this is the GHOST tree for that FICO data set. So let's take a look at it. So what this model says is if the external risk estimate is too high or too low, right? If the value is too high or too low, then we know what the prediction is. Okay, so no default or default. But if the value of the external risk estimate is in that kind of sweet spot, the same one we saw in the previous model, in the fast sparse model, if it's in this like little sweet spot, then you have to ask these more detailed questions, like how many months since the most recent inquiry, and excluding the last 7 days, right? You have to ask about % of trades with a balance and so on. So I just want to point out how difficult this kind of model is to create, right? Your algorithm has to figure out all kinds of stuff, including all of these thresholds, like these numbers here, where to put each of the variables, even the size of the tree, you know, which branching, what kind of branching you're going to do. It's actually really computationally hard to do this, right? Even if you're familiar with computational hardness categories, this problem is NP hard with no polynomial time approximation, and yet it was created by GHOST in 8.1 seconds, which is really impressive. Now, this tree over here, this is actually the same tree as on the previous slide. It's just displayed in a more artistic way. Okay, so this year my lab participated in the Bell Labs prize competition, and we needed a really beautiful title slide. And so this slide was designed by an artist friend of my collaborator, Margot Seltzer. And so that's why it looks so cool, like this like kind of predictive model kind of growing in nature. So I find interpretable models much more natural than black box models, right? Black box models might be some kind of like snarls of branches or something like that. All right, so what we found, like I said, is that even on these competition data sets, even on these data sets that are known to be really, really difficult, we're finding interpretable models. Now, if people are not using interpretable models, what are they using, right? They're using black box models. So black box models are too difficult for they're either too difficult for humans to understand, or they're proprietary. And if they're too difficult to understand, they definitely cannot be put on a PowerPoint slide. So what's wrong with using black box models? So first of all, they're really difficult to use in practice. So here's an example from criminal justice where a typographical error in someone's risk score calculation ended up denying them parole. And that meant that a typo determined someone's freedom, which is not how the criminal justice system is supposed to work. Also, black box models are very difficult to explain. So here's an example for on loan decisions. So, if your loan is denied, you might not be able to buy a house, and you want to know why that's happened. And so a lot of people are trying to explain black box models, but those explanations are not sufficient. You actually want to know the calculation for what led to your loan being denied. Also, black box models are really difficult to troubleshoot. I have here an article from the world of healthcare where you've got a deep learning model that's supposed to detect intracranial hemorrhages. And it was approved by our Food and Drug Administration to be used in practice. And then they launched it in practice and it didn't work and nobody knew why. So healthcare is actually a huge can of worms. So black box models in healthcare deserve their own slide here because they just cause so many issues. Like, for instance, you often have the situation where the model is right, but for the wrong reasons because of some correlation, like predicting that someone won't have a good outcome based on their x-ray. But instead of looking at the x-ray, the algorithm just looks at which machine the person got their x-ray taken on. So, the medical decision ends up being based on which x-ray machine the person got their picture taken on, which is not good. But since you don't understand the reasoning process of your black box, you just don't know whether this is what's going on or not. Also, you've got all these high stakes decisions. You really don't want to leave these high stakes decisions to a tool that doesn't really understand the whole situation. And then there's a lot of issues with troubleshooting. Troubleshooting is so difficult when you have a black box because you can't second guess its reasoning process because you just don't know it. Right? So is it going to work if I switch equipment? Will it work for all types of patients? Can I check if it's working on my current patient? Is the information that I fed into the system correct? Right? And all that stuff becomes difficult when you use a black box. There's also issues with responsibility, right? It's the doctor's responsibility to make a good decision, right? This is about accountability. Who's making the decision here? Is it the human or is it the machine? Right, so black box models, they essentially turn what would be computer-aided decisions into automated decisions. And so black box models really shouldn't be used in healthcare if at all possible, unless they are like 100% accurate or unless their result is easily checked or something like that. All right, so if black boxes are bad, why do people still use them? Well, what I found is that people actually don't believe that interpretable models can be as accurate as black boxes. It doesn't matter how many examples you give them. When a new problem comes along, they still go, oh, this is probably something that needs a black box. Now, I can understand this for domains that sort of really benefit from neural networks like computer vision or speech. But even if it's in a domain that's never benefited from neural networks, people still think like this. Also, people really like black boxes. Black boxes can be someone's secret sauce. You can sell a black box, right? You can't really sell something that fits on an index card, right? You got to sell the mechanism to collect all that data from patients and combine it behind the scenes and so on. Now, interpretable models are also, as I showed you, they're kind of hard to create. I'm hoping that this talk will convince you that they were hard to create, that this was in the past, but that's the point, that, these problems are constrained optimization problems that are very technically difficult. Now, anyway, I'm not sure that I can handle the politics on the secret sauce thing, but I can definitely help with the first one and the third one. So I want to discuss this third one first, okay? The fact that interpretable models were hard to create. Okay, so the reason they're hard to create is because of the interaction bottleneck that arises when people realize that interpretable models have interpretable flaws and they need to fix them. So let's say that a doctor uses data to produce an interpretable model, okay? So the doctor looks at the model, which is now possible since the model's understandable, and they find that it doesn't align well with what we know about medicine, okay? So what do? Right, the machine learning algorithm gave them this model, and so the doctor is stuck. So even if there were hundreds of millions of equally accurate models, the algorithm only returned one of those models, right? These models, they're all equally good with respect to the data, right? With the data you've got, there's literally no way to tell which of these models is better. The only way to tell the difference is with domain knowledge, but there's no easy way to put the domain knowledge into the algorithm. And this is a real problem, that there's no feedback loop, right? Machine learning algorithms, they produce one model at a time, and interacting with machine learning algorithms is a problem that the standard machine learning framework is just not equipped to deal with. And so we realized that we need an entirely new paradigm for machine learning at this point, because it's just totally broken here. All right, so my collaborators and I decided that the standard machine learning framework just had to go. So last year we produced a new paradigm for machine learning. It's something that's more human-facing than standard machine learning, which is to hand the user not just one good model, to hand them all good models from a given function class, right? Not just one, and let them choose which model they want, so that they can pick something that doesn't just agree with the data, but also agrees with their domain knowledge, so they might actually use it. And the set of these good models, we call this the Rashomon set. Now, I want to point out that doing this is extremely technically difficult. As I pointed out to you earlier, finding even one optimal sparse model is provably hard. But now I'm saying that we have to find all of them and store all of them, even if there are hundreds of millions of them, and we have to visualize them so the user can choose from them. So this is really not easy from a technical perspective, but it's extremely useful in practice. And it changes the whole notion of machine learning from just optimization to enumeration and storage of the Rashomon set and visualization of it. So let me show an example of this, because we now have the first algorithm that computes the whole Rashomon set for a non-trivial function class, which is sparse decision trees. And like I said, so Margot Seltzer and I and our students, we've been working on variations of optimal sparse decision trees for over 10 years. And now we can solve these optimal sparse decision tree problems very quickly. So I'm just going to put up another ghost tree. So this is a ghost tree on a criminal justice recidivism data set. So here this says, well, if you have more than 3 prior offenses, predict arrest within a couple of years of your risk score calculation in the police station. Otherwise, ask about the age, and so on and so forth. Okay, so that's the way these decision trees work. And the algorithm in this new paradigm, it's called tree farms. And it finds, like I said, not just one optimal sparse tree like Ghost, but it finds all the optimal and slightly suboptimal trees for any reasonably sized data set. And it displays them in this interface called TimberTrek. So I want to just show you how TimberTrek works. So I'm going to just switch my screen sharing really quickly over to showing you TimberTrek. Let's see here. Oh, interesting. Zoom is being interesting. All right. All right, let me try again. Let's try this. We'll try doing it this way. Okay, cool. All right. Got it. Okay, so this is just TimberTrek loaded with this criminal recidivism data set. This is the famous Compass data set. And each of these gray bars is a different decision tree from the Rashomon set on this data set. So all these trees are equally good with respect to the data. The only way to tell the difference, again, is domain knowledge. And so if you want to just, like, let's say you want to explore this Rashomon set and you really want to look at only the trees where the top split is, the first question we ask people is the number of prior crimes greater than 3? So if we click that, then it just limits us to just trees where the number of prior crimes is greater than 3. Okay, so maybe I could I could take a tree, I could store it, I could put a little heart on it, like I like this. I could write a little note on it, like I like this tree because it has this nice property that I want. Anyway, yeah, so you can store lots of these trees if you feel like it. And then let's say you want the second question you ask to be whether the age is less than 26. And so you can, again, restrict yourself to that and then just get trees from there. So another thing you can do if you have the Rashomon set is you can handle constraints really easily. So something like algorithmic fairness, like if you want your model to have some kind of algorithmic fairness property, that would have been very difficult before because you would have had to take your fairness criteria and put it into the optimization problem and solve it. Whereas if you have the whole Rashomon set, all you have to do, so let's say, for instance, that you wanted, let's say that you had a sensitive variable, which is whether the sex equals female. you can just uncheck this, and all the trees that have that variable are now gone. And you can do this kind of filtering step for any algorithmic fairness criteria. So you can just filter the Rashomon set to just the models that obey that fairness criteria, for instance. So it just makes working with these data sets like much easier than ever before, and it just really helps solve the interaction bottleneck. Okay, so let's go back to slideshow here. All right, cool. So the nice things about this setup, like I said, there's no more interaction bottleneck, and it makes constraint handling, right, really, really easy. So the feedback loop to humans, essentially instantaneous, and these constraints like fairness, like monotonicity, like if you want the model to increase along one variable, right, you can do all that very, very easily. So because tree farms did the hard part of finding all the good models. It's just like a filter operation now to incorporate constraints. So it's very easy to do. Okay, so I hope you're starting to see the value in this new paradigm. It's a lot more computation up front for the algorithm, but it completely annihilates the interaction bottleneck in constraint handling. All right, so let's see here. Whoops, let's click this one. Okay, so we've at least made a lot of headway in fixing this third issue, which is that interpretable models can be hard to create. So let's switch gears toward the first issue, which is that people just don't believe that interpretable models can be as accurate as black boxes. So what in the world would convince these people? Right, so I figured, look, I've been presenting examples from real data sets about the existence of interpretable models for a decade, and they didn't believe them then. And so, and they still don't believe them. So if they don't believe the evidence from data sets, I thought maybe I could try to convince them with a mathematical proof. So the goal became to prove that interpretable models are likely to exist for data sets with specific characteristics, right? That way, by knowing something about how your data is generated, you should be able to know right then and there, before running any algorithms, whether this is likely to work, right? In order to get us, okay, so great. So in order to get us into the right frame of mind for this, we're going to talk about the universe of supervised machine learning problems. Okay, so there are really two different worlds of machine learning based on the kind of data that you're working on. So most people think these two types of problems are the same, but they are fundamentally different, which is probably why people are getting confused. The field of machine learning has mostly focused on these raw data problems like vision and speech and language. And here you can make really complex models like deep neural networks, and they actually generalize between the training set and the test set. But for tabular data, which is the kinds of problems I've been showing you, right? The kind of problems where the data go into a spreadsheet, right? For those, if you try to use a really complicated model, it's not going to work. It's just going to overfit. And you're not going to see the benefit of the extra complexity. Now, there's one important difference between these two problem types, which is that raw data problems have outcomes that are certain. So for image recognition, for instance, we know whether an image contains a chair, for instance. So it's possible to get over 99% accuracy in identifying chairs. But most data-driven problems in the world are not like that. They have uncertain outcomes, like the FICO dataset. And for another example, consider two medical patients with almost identical medical histories, right? One could have a heart attack next year and the other one might not, right? And deep learning really hasn't had an impact in these kinds of problems, right? And I believe I understand why it can't. And it's not about whether we have the right algorithms. It's just something different about these problems that allows us always to find accurate, simpler models for them. So here's like a simple visual example in 2 dimensions. So here's a clean data set where you can fit the data perfectly and everything's fine, right? As soon as you introduce a bit of unpredictability, what we call noise, then boom, you overfit. All right, so Lesya Semenova, Ron Parr, and Harry Chen and I have written these 2 papers, which together aim at least to give some semblance of the beginning of a mathematical proof that noise actually causes this whole thing, right? Uncertainty, noise, that's what leads to large Rashomon sets. And large Rashomon sets lead to the existence of interpretable models. So I'm going to show you a picture at the bottom so you can kind of see what I mean. So here, this is a noisy data set, and here's its Rashomon set. This is the set of good models for it. And so here's like a clean data set, and here's the Rashomon set for that. And you can see the Rashomon set seems to be bigger for these noisy data sets than it is for the clean data set. All right, so you can get the idea kind of intuitively. Now, the theory is a little bit hard to understand if you're not a machine learning expert, but I'm going to try to explain just like a drop of it, okay? There are a lot of theorems and proofs that go into these statements that I'm saying. It's going to sound like an abstract hypothesis, but actually we actually know that these things are going to be true in important cases. So the way it starts is that noise in the world leads to increased variance of the outcomes and increased variance of the error in the error in the algorithm, prediction error. So I used to think that if you took a clean data set and you added a little bit of kind of uniform noise to the data, then the predictive error for all the functions would just go up by an equal amount, and the set of good models would still be the same, and the set of bad models would still be the same. But that does not seem to be the case. In fact, it's just totally not true. So when you add noise, the error definitely goes up, but what happens is that you can't estimate very well what's going on because you have this variance in the world. So all of a sudden you just can't see anything. It's like you're in a cloud of uncertainty smog. And then this higher error variance leads to worse generalization between training and testing. And this makes it much easier to overfit the data. So again, you just end up in this situation where when you have, this noise, you just tend to overfit. Okay, but the analyst who's working on this problem actually sees the issue because they have a holdout data set. They're doing some kind of cross-validation. And so they see that fact that the model's overfitting, and then they simplify the function class. And so now they're working with simpler models than they were before. Okay, when the analyst simplifies the function class, the new function class, the simpler functions, have a larger Rashomon ratio, which means that the fraction of good models is larger. Okay, so why is that? So it turns out that if you go to more and more complex function classes, you've got more good models than you did before because you've got more models than you did before. But the thing is that the total number of models goes up really, really fast. So the denominator in this fraction just blows up. You can actually kind of see it with decision trees, right? The simpler class is small decision trees, and the more complex class is larger decision trees or deeper trees. And so what happens is that the good smaller trees, they can also grow into good larger trees, but they also grow into a lot of bad trees, since there are usually a lot of bad options, but not as many good ones. And the set of bad trees, it doesn't really grow into good trees all that often. It actually grows into bad trees much more often than it grows into good trees. Okay, so you've got the set of good models being large relative to the size of the function class. And now that actually was the key step, because once you have a large fraction of good models, then the set of good models, that's likely to contain at least one simpler model that's still good. So think about it like shooting at a target, right? If the target's bigger relative to the size of the board, you can hit it much more easily, right? So there's your simpler model, right? There's your simpler model, it's right there. And so you have a simpler model that's also good. Now, that was the last step of the proof. As I mentioned, each step is backed up by a theorem or several theorems that shows that in special cases, these things actually hold. And one nice thing about this whole path to simpler models is that the practitioner never actually needs to know how much noise is present for this to work. It just happens, okay? So what I'm saying, is I've showed you the Rashomon set theory, and the implications for this theory are actually pretty intense, because what it means is that optimizing for simplicity in these machine learning models won't sacrifice accuracy for a vast set of problems. Right? It's any problem where there's noise and you can't predict perfectly. So you can just get a sense just by knowing one thing about how the data are generated, whether or not simple yet accurate models are likely to exist. Now, if I'm right, this has huge implications for a lot of high stakes decisions that are made using data in our society that deeply affect people's lives. And that includes criminal justice decisions that determine people's freedom, for loan decisions that determine someone's ability to purchase a home, or for medical decisions that determine life or death. Because if I'm right, then for none of these decisions can we really justify black box models. For none of them. And it's not like we didn't know this already. I mean, this right here, now interpretable AI models have a precedent in high stakes healthcare decisions. So this model right here, for example, that's the 2 helps 2B score, which predicts seizure risk in critically ill patients. This is the only AI model used in critical care brain monitoring, and it was developed by our lab. Let's talk about criminal justice. Do we really need black box models there? Now, my first paper on this was in 2017. So I've been studying this for maybe 8 years, and tiny little models do just fine for this, even on data sets that consist of over 40,000 people. So I don't see any good reason why we should allow black box models in the determination of someone's freedom. And for loan decisions, I already showed you models built on the FICO dataset. Both of these models were built in under 10 seconds, and they're about equally accurate to black box models like boosted decision trees and deep neural networks. Right? If the major credit scoring agency in the United States provides data that they don't think can be handled by interpretable models, and they are wrong, think how many other people are wrong about this. All right, so far I've showed you that even on competition data sets, we find interpretable models. I've shown you the Rashomon set paradigm, where the goal is to find Rashomon sets and not just some single models, which solves the interaction bottleneck and also makes constraint handling very easy. And then I also showed you this proof we called it the path to simpler models starts with noise, right? This is the proof that simpler models exist. And the way it works is that trying to predict outcomes that are uncertain leads to large Rashomon sets. Large Rashomon sets imply that simpler models exist. Okay, and then I pointed out that this has huge implications for criminal justice, loan decisions, and other high stakes decisions. So where do we go from here? Or at least where do I go from here? So, I think one thing that our work could really help with is regulation, because I really think that we should have no black box models for high stakes decisions that deeply affect someone's life unless there does not exist an equally good interpretable model. And we know that, that's not very likely to happen for problems with uncertain outcomes. Also, the performance comparison between the black box and the interpretable model should be done in practice and not on a static data set. So it should be done, this comparison should be done considering the whole system, not just the predictions, but also the ability to troubleshoot and correct the inputs and so on, because that will really show the advantage of using a model that people understand, because then they could troubleshoot it. And also, we should not have any, no more stupid explanations of black box models. We don't just want to know which variables are important. We should be able to demand to know exactly what went into that decision. But regulation is taking too long, right? At least, Europe is kind of moving on this. I was happy to see President Biden's executive order recently, but it's really only a start, and we don't truly have any real regulation of AI at all in the United States right now. So anyway, we're not just going to sit around waiting for regulations in order to do something. So what I'm working on right now is expanding the Rashomon set calculation to include additive models, and also using the Rashomon sets for variable importance calculations. So we call this project XAI, so explainable AI on steroids. So we've designed a variable importance measure called the Rashomon importance distribution, and it's trying to estimate the true variable importance. So the variable importance for the data generation process, and not just sort of one predictive model that somebody creates on a data set. And it works by averaging variable importance information across, the Rashomon set and across bootstrap. So kind of data sets that are slight variations of the original data set. And it's a much more holistic view of variable importance. And so just adding the capability to create interpretable models and understand which variables are important, I think could really make a difference. One important project in our lab is about risk scores. So this is the latest method in our lab that produces risk scores. The method's called faster risk. So risk scores are like the 2 helps 2B score that I showed you earlier, or the CHADS 2 score, or, of these popular models used in medicine, like the APGAR score, right? So these are sparse generalized additive models with integer coefficients. So scoring systems, they're very simple model forms. You just add up some points, and then the total score translates into a risk using the table here. But risk scores are notoriously hard to construct because you have to have only a small number of variables, and you have to have integer coefficients, which that makes it sort of doubly hard. So this is faster risks result on that FICO data set that I was showing you earlier. So this model loses a little bit of accuracy compared to the FastSparse and Ghost models that I showed you earlier, but it's so crazy simple. I mean, look how tiny this little model is. Anyway, it's still pretty accurate. I mean, compared, considering how really, really tiny this model is. We have a bunch more methodology work going on besides what I just showed you, but let me switch to some applications that we're working on. So we're working on material science, where we're trying to use interpretable machine learning to guide the search for new materials toward patterns that humans can understand, so it's easier to sort of look through the space of materials. We're specifically working on metamaterial design. And then I still work with the neurologists that I've been working on for the last decade, the same ones that I worked on to design the 2HELPS-2B score with. And what we're doing now is trying to figure out drug or treatment regimes for patients. So which drugs to give them and how much based on what we're seeing in their EEG patterns, the brain measurements that are being taken all the time of these patients. And then I have a group of students working on dimension reduction for data visualization, where you can take high dimensional data and project it down to low dimensions to be able to see what's going on in it. And this seems to be very, very useful for genetic data. And then we're also working on studying the combination of cannabis and HIV and how it affects the immune system of people with HIV, because a lot of people who have HIV also use cannabis. And then we also have a group of students working on interpretable neural networks. So these interpretable neural networks, they use case-based reasoning, where they have to reason about some new signal based on its similarity to parts of the training examples. So here we're using it for neurology, and then here we're using it for computer-aided mammography. It's kind of like, it's case-based reasoning, so it's kind of like K nearest neighbors. It's like what a doctor would do, where they go, something, I've seen that before. It's, I've seen a patient 20 years ago that had that thing, and it's kind of like that. So it's kind of like, anyway, I can't resist going into a little more depth on interpretable neural networks. And so the way they work is that they create a score for how much a part of a test image looks like parts of prototypical training images. So here, for instance, it's saying, why is this bird classified as a clay-colored sparrow? So the network says, well, it's because this part of the bird, highlighted in these two different ways, looks like this part of that bird. And I know what that bird is. That's a prototypical clay-colored sparrow. And this part of the bird, like the belly and the edge of the wing, look like this part of that bird. And that's also a prototypical clay-colored sparrow. And this looks like that, and this looks like that. And so that's why I think, this is a clay-colored sparrow. And each of these comparisons get some point score, and the points get added up, and that's how the algorithm works. And we do the same thing in computer-aided mammography. So here we have a breast lesion. We're trying to figure out whether to biopsy it. And so the algorithm is saying, well, I think this part of the lesion looks like this part of that lesion, and that's a prototypical indistinct margin lesion. And this looks like that, and so on. And so then the total information from all of these comparisons can be used, and the radiologist can check every single comparison to see whether it really makes any sense. All right, so a couple more applications. So I also work on heart monitoring with wearable devices. These are really going to impact our ability to understand heart health for the whole population. So we have these interpretable algorithms that are designed to analyze that kind of signal. And then also, I have a team that works on interpretable AI music generation. We actually don't use neural networks at all for this problem. We actually use other AI techniques combined with our knowledge of music theory. So all these topics are super interesting, and it just really shows a hint of what you can do with interpretable AI. All right, so the takeaways are that a vast number of real-world problems do not benefit from black box models. They do not, they cannot, and they never can. Now, I've shown you both empirical and theoretical evidence, including something like a proof that interpretable models should exist for noisy problems. I think regulation is needed to prevent abuse in high-stakes problems because companies really like to inflict black box models upon people in high-stakes situations. And finally, AI holds endless possibilities for brightening our world and helping us to make better decisions by aiding us without replacing us by black boxes. Thank you very much.
Thank you, Cynthia. That was great. We count on you and colleagues on unleashing all the possibilities for the practitioners like us. So thanks. That was great. I want to. We have a bunch of audience questions, but I want to start with a slightly philosophical question, which is, so when you say that we should only employ explainable models, so we humans can understand it. Why would you agree that maybe black box models that we don't understand could sort of be beyond what we humans can explain? Why would you limit models to only be within our own mental explainability framework?
Okay, so I just spent 37 minutes trying to describe that to you, so clearly my message did not get across. So you have issues where, like there's no database that's actually perfect. Like I've never met a large database that's perfect, particularly in healthcare. I mean, you've got scrubs on, right? You know that how messy medical data are, right? So if you're going to trust a black box on a medical data set, you're crazy because what you're doing is trusting that all of the data put into that data set was like perfectly constructed, because if not, you're going to have machine learning models that depend on the type of X-ray equipment rather than the actual medical content of the X-ray. You're going to have, typos in the input data causing, you to make decisions on just on, mistakes. You're going to have a lot of like the models based on medical notes with wrong timestamps, and so you could actually end up predicting things that have already happened, and that happens a lot in with medical data sets. And so that's why you need a human to really like look over what's going on, because they can't, if the black box model, they can't check if it's working on their current patient, they can't check if the information they put into the systems, right? Like it's just not trustworthy. I mean, there are some applications where black box AI is totally fine and it saves a lot of time, but those are cases where it's 100% accurate. Like, can you detect if there is any lesion in this image at all, right? If it doesn't detect a lesion, what's the explanation? I can't find one. There's nothing in this image, right? Yeah. But when it comes to like biopsy decisions or these other kinds of very high stakes decisions where, yeah, or like.
No, I know where you're coming from. No, I totally agree. Okay. No, I totally get it. And I'm also, I agree that if there's any models making decisions for my patients, I do want to understand where they're coming from. But I can also see that, there's many tests, many lab tests, imaging techniques that we use where probably I don't really understand how they work, but I trust that they're, sort of well validated and regulated. And I think that's kind of the point, right? And that's what you also alluded to. There will be applications where you need deep learning, like images, large language models.
Well, hold on a second. Let's not equate machine learning models, which are predictive models, with deterministic systems like cars, right? I don't need to know how my car works to trust it because it's just a mechanical system, right? We're talking about machine learning models that are built from data sets that are noisy and messy and created often by humans or, messy stuff. So, these are two very different situations, and you can't equate black box anything with black box machine learning models. So let's not do that there.
Okay. All right. So Sana Chala was asking, I think she's asking, so interpreted models may have different applications than black box models. Yeah, do you kind of discussed that already, or do you want to add the different applications?
Yeah, so like I said, so there are some applications where black box models are totally fine, right? If you want to have a black box model scan an image to see whether there is blah in an image, right? That's super helpful if the black box model can just find it for you and then human can verify it, that's there. That's great. But when you're talking about these high stakes decisions that, where where like with biopsy decisions, a radiologist needs years of training to actually understand what's going on there. I cannot read those mammograms. Like it's impossible for me to read them. I rely on my radiologist collaborators because they actually need to know what's actually going on in the image. Loan decisions are based on a lot of factors, right? So, and a lot of that, I don't know about you guys, but often the data in those databases are messy, like they're not correct, and it's really hard to like fix the data in those databases. So you've got to have a human checking everything, making sure everything's fine. Criminal justice decisions, right? Oh my gosh, talk about messy data sets, talk about messy decisions. Yeah, so yeah. Okay, yeah, so let's go to the next one. So formal definition of interpretable. So I do have a formal definition in, we wrote a review paper a couple of years ago called like 10 fundamental principles and 10 grand challenges for interpretable machine learning. And it's basically, you're adding constraints to a model so that humans can understand it. And there can be like a different range of these constraints based on the domain. So different domains, what's interpretable in one domain is not necessarily interpretable in another domain. One type of interpretability one type of interpretability constraints that seems to transcend across domains is sparsity, because humans can handle only 7 plus or minus 2 cognitive entities at once. And so if you have a model that only relies on a small number of factors, it's much easier to troubleshoot and use. So we generally try to construct small models like I was showing you in the talk. But yeah, for other domains that wouldn't make sense, right? So you have to think carefully about matching your interpretability metric to your domain, the same way you have to measure your performance metric to the domain in machine learning. Like a lot of domains, you can't use accuracy, because accuracy, like that's, if you have a very imbalanced data set, like we're only a small number of positive examples, right? Then you can't use accuracy because everything's 99% accurate. So you have to use a different metric. So it's the same thing with interpretability. You have to choose the performance metric and interpretability metric to match that domain.
So maybe let's now give the word to David. Maybe David, you can take the next question, and then Michael Spicer. David, I think that's also in your interest. You can lead up to his question later.
Yeah, thank you very much for this very interesting talk. And I totally understand the benefit of having interpretable models. But let's for a second just imagine that there will be a prospective trial in the future where we have an interpretable model competing against the black box model. And on average, the black box model outperforms the interpretable model, maybe even by a small percentage.
Okay, so I don't know where you came up with that, because I just showed you even a mathematical proof that doesn't happen. Like okay. I'm telling you, you just totally proved my point in the talk, that it doesn't really matter how many times I prove this or how many data sets I show or whatever. People just still don't believe that. They have to believe that if you add more complexity, you're going to get better predictions. But it just doesn't happen with noisy data sets. And in fact, the opposite problem happens, where if you use a black box and people can't troubleshoot it, then in practice, the black box is less accurate than the interpretable model. So you're putting out this kind of like, false dichotomy that it's just purely not true. I mean, you can keep going on with it, but I'm just going to repeat what I said before, which is that, here I've showed you these, for tabular data, sparse models do just as well. For neural networks, these interpretable neural networks are just as good as the black box neural networks, but you can troubleshoot them. So you can keep going, but you're not going to get anywhere with me, because I've seen it.
Okay. Yeah, I'm already convinced. I'm just trying to maybe just come up with some challenges to this point of view. But yeah.
So everybody does this. They always construct this false dichotomy. They're like, what if this is true? You got the black box and it's more accurate, and the interpretable model is not as accurate. No, that's false. It's just a false dichotomy, and you should just stop right there. It's the other way around. What if there was an interpretable model that's more accurate than the black box? Which would you use? Yeah.
Okay, so I'll take the next question from one of the viewers, and actually had the same question or a similar one. Can you comment on how causality figures into interpretability of models for tabular data, and are causal relationships and hypothesis consideration in your work?
Okay, so that's a really deep, insightful question there. One of the labs that I co-lead is a causal inference lab called the Almost Matching Exactly lab. And what I've learned from working in causal inference the last several years is that, you know, you in order to make any kind of causal conclusions from observational data, you need to have a ton of assumptions. And so I carefully avoided all of those assumptions and carefully avoided saying anything about causality in the talk. But one thing you can do if you want to do causal inference is, okay, so here, okay, sorry, I have so many different directions I'm trying to go in all at once to answer this question. Great. So the first thing I should say is, you know, we're working with observational data here, so a lot of people don't consider anything causal unless you do an experiment. Okay, let's put that aside. Now, if you're going to do observational causal inference, you need all these assumptions like SITVA and overlap and all this stuff. So let's say you have those assumptions. One thing you can do that our lab has been doing for observational causal inference is to do matching. So what you do is you take, you want to find the effect of a treatment. And so you simulate a randomized control trial by taking a control unit and an almost identical treatment unit. You match them together, and then you try to estimate the treatment effect by looking at the difference between the outcomes. And you can do this by constructing this, you know, you take your large observational data set and you put it into these matched groups, and then look at the outcomes in the treatment units and the control units, and then take the difference. And then from there, you can use these interpretable machine learning algorithms that I presented to try to understand the treatment effects for the different subpopulations. So that's one way to do some kind of observational causal inference on the data. One warning that I need to give, so just switching topics here, one warning that I need to give is that sometimes people look at interpretable models and they interpret them as causal. You cannot do that unless those models were actually designed to be causal. Okay, so then that's the second bit. Okay, the third bit is that, you know, you can use interpretable machine learning models to, in a reinforcement learning setting, to do interpretable policy creation. And so we have papers about that as well. And then I guess the last comment I have about this is that the variable importance stuff that we're doing is somehow aiming at causality, although we're not exactly sure how. So for example, with the genetic data, I mentioned a project that I'm working on in HIV and cannabis, and we're trying to figure out which genes are sort of important for HIV latency. So it's kind of a causal question, and if you can do the variable importance calculations right, we might be able to figure out something causal about these genes. We've actually picked out a specific gene that hasn't been found before that we think might have some kind of causal relationship to HIV latency, and so that's another connection to causality. Okay, long answer, sorry, but it was an important question.
It's also a very complex topic, yeah. Thank you. Matthias, do you want to take the next one?
Sure. So Jesus Castañeto is asking if you've applied your interpretability approach to health surveillance of emerging infectious diseases.
No, we have not. Doesn't mean it's not possible. It's just something that I don't have a collaborator who's doing that, and we don't have a data set in that. So yeah, just hasn't happened. But all of our code is public. I should say that all of our code's public, and so if anyone wants to use it for any of those questions, they can. And we always try to provide help for anyone who runs into any kind of coding issue or has a question for us.
So as a practitioner, there's lots of you know, like PR coming at us about like all the big language models, you know, that will sort of be implemented for us to use in be it speech to text, you know, and that's probably something that it's not really important to have explainability, but you know, there might be other applications. And I know that it's super challenging to apply any sort of explainability techniques to these LLMs, and I'm just interested in your take on this.
So I don't work on large language models. I have not worked on NLP very much, simply because, like you said, it's not high stakes, and so I've been working on it. But I have a bunch of former students who work in NLP, and a bunch of them have started working on interpretability for large language models. And I asked them, like, why are you doing this? And they said, no, it's actually really important because we can't control these models and we can't troubleshoot them, so we actually need that. So I think interpretability might be able to help with troubleshooting and stuff like that. It's just not something that I particularly do in my lab.
Okay. Yeah. All right. So I think, David, do you have more questions? Then please go ahead.
Just another question concerning the causal modeling. I mean, often the causal graph is used to then come up with a set of confounders that you want to adjust for, and then some very basic statistic models are often used for that. Have you worked on the combination of using a causal graph or these assumptions, feeding them into these more advanced models that you're working on?
So you meaning like the Pearl framework? So we work in like the potential outcomes framework. So that's easier for us because you can put in covariates. So yeah, I guess we're really more focused on potential outcomes. Yeah.
All right. So I don't see any more audience questions coming in. Then I'd suggest we're almost at the hour and we move over to the neural network and be chatting there. Cynthia, thank you so much for joining us today and for putting forward why interpretable models should always be used. That was really interesting. I learned a lot. And also on behalf of David, on behalf of AI for Good, thanks for joining us. And yeah, looking forward to see you online in the neural network. Goodbye, everyone.
Thank you.
Thanks. Bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.